Hello, hello, hello. This is Coach Ikram, and welcome to this video on the periodic table of the elements. In this video, we're going to talk about a brief history of the periodic table, its organization, and how we use it. Let's start by talking a little bit about history. Mankind's been discovering the properties and uses of elements for thousands of years. And over about 350 years ago, various scientists began to discover, list, and classify these elements in order to better understand their relationships with each other and better understand how they can be used and reacted. For our intents and purposes, we're going to talk mainly about two scientists, and they are Dmitri Mendeleev and Henry Moseley. Dmitri Mendeleev organized the first modern periodic table, and he did it by organizing it by atomic mass. Has allowed him to create a periodic table that allowed room for elements that hadn't been discovered in his time to potentially be fit into blank spots in his periodic table. Then in about 1916, Henry Moseley, following the discovery of the nucleus, he was doing research, and his research ended up showing the significance of the atomic number, which previously until this point had kind of been thought to be arbitrary. And he discovered that if he organized the periodic table by atomic number, it set the periodic table up so that the relationships were more clear. And to this day, that's what we use. Our modern periodic table is ordered by atomic number, which is Moseley's contribution to the periodic table. So as you go down the periodic table, atomic number increases, starting with 1 with hydrogen, 2 with helium, 3 with lithium, and so on and so forth. So now we're going to talk about how the periodic table is organized. And we're going to start by talking about the groups in the periodic table. These are going to be your vertical columns in the periodic table that go like so across the periodic table. They're designated by numbers 1 through 18. 1 is on this side, 18 is over here over the noble gases. The group numbers 1's place represents the number of valence electrons that an atom possesses. But this is only going to apply to these groups right here. So for example, if you've got group 16 over here and group 17, those have 6 and 7 valence electrons respectively. And it also works for groups 1 and 2 over here. They have 1 and 2 valence electrons respectively. So the valence electrons that we're discussing are the electrons in the outermost energy level of the atom, and this is what's going to be responsible for bonding. As you go down each level in a group, so as you go down the periodic table in the group right here, an energy level is added to the atom with each element in a group. Each outer energy level is going to be repelled by all the levels of core electrons underneath, because remember, they're all negatively charged. So the outermost layer is going to be repelled by everything that's underneath it. And elements in a group have similar physical and chemical properties, and that's really important to understand once we start talking about these families and these groups in the periodic table. So the second way that we're going to organize the periodic table is by periods, and that's these horizontal rows right here. And they're going to be designated from numbers 1 through 7, and those are those energy levels. And we've previously talked about those when we did electron configuration. And the energy levels, remember, they're a space. They're not like a level in the way that you saw in the Bohr model. They're a space around the atom's nucleus where electrons are confined based on the amount of energy that they have. From left to right in a period, as you move across, like you're reading a book, each element will gain 1 proton and it will gain 1 electron. And as you go across, because you're going from group to group, the properties are going to change from left to right. This little zigzag line that you see on the periodic table, that's going to separate your metals from your nonmetals. So your metals are going to be on this side of the periodic table, and your nonmetals will be on this side of the periodic table. So metals, remember, we said are going to be on the left-hand side of the periodic table. They tend to lose electrons and form what we call cations. Those have a positive charge because they've lost 1 or more electron. For example, sodium with atomic number 11, it loses 1 electron to become the sodium cation, Na+1. Nonmetals, over here on the periodic table, they're going to tend to gain electrons, and they're going to form anions, which have a negative charge because you've gained 1 or more electrons. So for example, sulfur, it's going to gain 2 electrons, and it's going to become sulfide. You can't really see on it, but it would look like that. Metalloids are going to have properties of metals and nonmetals, so we call them semimetals. They're found along and to either side of the zigzag line right here on the periodic table, except for aluminum, which is going to be a metal. They're mostly brittle solids. They're going to be semiconductors, which means they conduct electricity well, but they're not going to conduct heat well. So now we're going to talk about the representative elements, groups 1 and 2, and then 13 through 18, and we're going to do it by group. So we're going to start with the alkali metals. They're right here on the left-hand side. They're in group 1, and their generic electron configuration is going to be their energy level, and then S1. They have one valence electron, so they'll lose that one valence electron to form a +1 cation. They're extremely reactive. They're never found free or not bound in nature. They have to be bound with something else in nature. And generally, they're going to be stored under oil to prevent oxidation. Alkali metals, they're extremely reactive. They react with H2O. They are soft and silvery, and they're used in soap, lights, and batteries, among other things. The second group we're going to talk about is the alkaline earth metals. They are S2, and they have 2 valence electrons, so when they give those 2 valence electrons up, they're going to form a +2 cation. They're very reactive, although they are less reactive than group 1, the alkali metals. And generally, they're also stored under oil to prevent oxidation. Then we're going to skip over here, group 17, and that's S2P5 is that generic electron configuration. And these are the halogens. They have 7 valence electrons, so they're very close to that octet. And they're going to gain 1 more electron to form a -1 anion. They're the most reactive of the nonmetals because they're so close to forming that octet and becoming isoelectronic with a noble gas. And some examples of them are chlorine, that's used in pool purification, iodized salt, and fluorine, which is used in dental health. Noble gases are this last group over here in the corner. They have 8 valence electrons, with the exception of helium, which remember will only have 2. They have a full outer energy level, and they are not reactive. They are happy, they follow the octet rule. Groups 13 through 16, they're named for the first element in each group. So for example, group 13 is called the boron group, because boron's at the top of that group when you're looking up and down. The properties vary depending on the group, and they'll have both metals and nonmetals, because remember, these fall on the metalloid line. The metals in these groups have variable properties, and the nonmetals in these groups will have also variable properties. The transition metals are this group right here in the middle, and that's going to be 3 through 12. They generally have multiple oxidation states, which means they can lose a different variable number of electrons, with the exception, remember, of silver and cadmium. We learned that silver always becomes +1, zinc and cadmium become 2+. Many of them are brightly colored, and they are found free in nature. For example, silver and gold are used in jewelry, and iron's used in steel. The lanthanides are going to be this first group down here. They are silvery, and they have a very high melting point, and they're extremely valuable metals. They're generally used in the glass industry and modern electronic devices. And remember, those are going to be the 4F if you're thinking back to electron configuration. The actinides are this bottom group right down here, and they're very radioactive. They're used in nuclear fuel, nuclear medicine research, and other nuclear industries. This is the end of the video on basic periodic table organization. Please rewatch, take detailed notes, and be ready to ask questions in class.